So last session we talked about finding derivatives. Actually, we have talked about that for last session and the session before. And we would also at some point like to find the derivative of exponential functions. And of course, the way to do this is to look at the definition. In this case, we are finding the derivative of an exponential function at the point 0, right? X is equal to 0. So here is a to the power 0 plus h, which is just h, minus a to the power 0. So we have an exponential function, and we divide it by h, which is some small number. So here you can see, and then we take the limit, then we get the derivative, which is the slope of this tangent line, right? And in this case, we have something very close to 1, and this happens for a equals to this, right? We can try decreasing the a. What happens? Well, clearly the slope becomes less and less steep. Agree? And if I increase it a lot, it gets very, very steep. Agree? And at some point, I mean, now it's more than 1, right? Before it was less than 1. So there should be some point where this actually is 1. Agree? Oh, now it's 1. So this happens at this magical point where a is equal to 2.7183 something, blah, blah, blah. And this continues at infinity. I mean, there are infinitely many digits in this number. Like with pi, like with square root 2. You cannot write it as a fraction. You cannot write it a finite fraction, at least. But anyway, this number e here is defined to be the number that has the property that at 0 it has the slope 1. It may at first seem like a strange definition. It turns out to be a very natural definition because a lot of nice properties comes out of this. Now that we know that the slope is 1 at 0, so we define the number e to be the number such that this limit states. That's what I just said. Now let's look at the theorem I've written over here. Here you see that if you take the derivative of this function, you get the function itself. There's only one family of function that has this property, namely e to the power x and any constant multiple of these. So if you multiply this by 2, of course it has the same property. That comes from the laws of derivatives that we have looked at already. If you multiply by 2, right, what is the derivative of a function multiplied by 2? Well, it's just 2 times the derivative of the original function, right? But in principle, one could say this is the only function that has this property, that if you take the derivative of it, you get the function itself. That's a nice property. There are more nice properties to come, but then we can use the chain rule on this function with this knowledge, and we will see that if we take the derivative of this, we just get the k down, right? Because take the derivative of the outer function, you get the function itself. That gives us this part. Where does the k come from? Well, what is the inner function? It's k times x. So if you take the derivative of k times x, you just get k, which is then multiplied onto this. So all we need to prove, I mean, I have said that this bit comes from the chain rule. All we need to prove is this bit up here. And all we need to know turns out to be that this is 1. So let f of x equal e to the power x. Then f of x plus h minus f of x over h is just this, right? That's just plugging into the definition of the function, what you have. Then we use one of the properties that we saw on the previous slide, that e to the power x plus h is just e to the power x times e to the power h. And this is not changed. But now we have a fraction where everything on top is multiplied by ex, e to the power x. So we can pull that outside in front. We do that, and then we're left with just e to the power h minus e to the power 0. As I've said several times, any number to the power 0 is 1. So this is e to the power h minus 1. Or it's just this, in fact, right? With a being equal to e over h. But this e was defined exactly to be the number having this fraction tending to 1. Agree? So this is a constant, doesn't change when h changes, and the other part tends to 1. So e to the power x times 1 is just e to the power x. So now we have defined our function, or our number e, such that it has derivative 1 at 0, and we've proved that using just that property, it will always be, at any point x, it will have itself as its derivative. So if you ask the exponential function, how fast are you going? It can just say, well, where am I, right?